Okay. Go away. Okay. So guys, again, starting over, we're going to do two things today. One of these is a formalizing of an idea that we've been talking about when we talk about what are called dilutions. Then, guys, I was sort of considering not doing this with you, but we're going to. We are going to talk about titrations. Had March and April not happened, this would have been the very last lab that you did last year. But guys, obviously after COVID, after we had our COVIDcation, we didn't do any labs. And so guys, you haven't seen this lab. So what I want to do is I want to introduce you to this. But frankly, the reason that I'm doing this is because if everything goes sideways and we do end up in permanent lockdown again like we did last year, I want to show you at least briefly how this software works. And then guys, if things really do blow up, I'm going to do what I can to try to get you guys copies of this software so that we can use it to continue to do labs. I'll explain more about that later. But for now, guys, just let me say, we were going to skip titrations, but now we're not. So, with that said, gang, let's dig in. So, no surprises, right? Molarity is moles divided by liters, huh? All right. You don't even need to write it down because you already knew that. But guys, when we talk about molarities being moles divided by liters, we now need to focus a little tighter on this idea of concentration. So guys, when we talk about concentrations, and I don't think you need to write this down either. Well, not yet. I'll tell you when to start jotting this down. Guys, when we talk about concentrations, there's two ways we can talk about this. We can talk about this as the concentration of solute first. So guys, for example, we have a 1 molar sodium chloride solution. We have a 1 molar calcium chloride solution. So how do you make these? Well, if you're getting a liter, you get a liter of water, add a mole of that, stir, boom, you got a 1 molar solution. But guys, we can also talk about concentrations of particles. And this is where I would encourage you to start writing, not words, but pictures. So guys, do this with me. Draw yourself a couple beakers and draw what is in a 1 molar NaCl and a 1 molar calcium chloride solution. While you're doing that, guys, I'm going to run over to the stock room really quick. I always convince myself I'm not going to do this, but it's worth showing you. I'll be right back. All right. Okay, so we'll play with that in a minute. But guys, let's talk about this now that you've had a chance to draw your pictures. So guys, remember a couple days ago we had this weird thought that says you've never tasted salt, right? And that there's no such thing as salt water. Because salt, as a strong electrolyte, when it goes into water, it ionizes. So what do we actually have in solution if we've got a thing of salt water? We've got Na ions, and we've got chloride ions. Now guys, what about calcium chloride? Let's just make sure we're clear. In a solution of calcium chloride, what exists in solution? What do we got over here? Calcium ions. So Ca2+. But then, guys, what else is in solution? The chlorine molecules, atoms, or ions? Ions. So how do we represent that? Is this okay? Are we clear on the idea that those chlorine atoms do not stay together as diatomic chlorine? Guys, we looked at pictures, right? These chlorine atoms are not bonded together in the crystal. They're on opposite sides of the calcium. When this dissolves in water, the ions are stabilized in solution. They do not come together. They don't form a gas. They don't go away. They stay dissolved in water. Is that good? Okay, now let me ask you a question. Look here. 1 molar sodium chloride, 1 molar calcium chloride. Which is more concentrated? Trick question. Which is more concentrated? They're the same. But now that we turn our attention down here, guys, which one is actually more concentrated? The calcium chloride. This is an important idea, you guys. When we talk about molarities, we can talk about them as solute concentrations. But what we need to get comfortable with is the idea that solute concentrations do not necessarily map directly onto particle concentrations. So when we break these into ions, it turns out that calcium chloride is actually 50% more concentrated when we look at the particles, because there's 2 chlorides instead of 1. Does that make sense? So now the question is this. Which one do we look at? Do we look at the solute concentrations, or do we look at the particle concentrations? And guys, the answer is the bottom. We talk about particle concentrations. So let me give you an example. Will these 2 solutions boil at the same temperature? Which one will boil at a higher temperature? The one on the right or the left? The right, because there's more stuff dissolved in there. Remember, guys, that right before COVID went crazy, we talked about colligative properties and this idea that when you add solutes to water, the boiling point goes up and the freezing point goes down. And that's all a matter of concentration. You guys even drew a graph when you add amount of salt and boiling point of water, and it looked like that. The more salt you add, the higher the boiling point goes. Guys, boiling point is a function of concentration, but even though these have the same molarities, this will boil at a higher temperature because it contains more ions. Does that make sense? You guys okay? Okay. So guys, that was thought number 1. We're now going to put this behind us unless... Oh, go ahead, Ronnie. Yeah. I'm not tracking with your question. Okay.
Wouldn't the NaCl have more ions, or have more of the original salt, before it was apart from the acid?
I understand what you're saying, but I'm not sure how you're coming to that conclusion. What about what you're seeing is intuiting for you that the NaCl would have more particles?
Well, it's because it has less ions.
Oh, no. So your reasoning is flawed. So here's the idea. Remember, I don't want to go back to the previous slide, but remember, molarity is moles divided by liters, okay? So just for conversation's sake, let's say we've got a liter of each, okay? So if that's true, that means we have a mole of this in a liter of water. But what is a mole? Well, it's 6.02 times 10 to the 23rd. So we have Avogadro's number of those in a liter of water. Same thing here. Here we have Avogadro's number of these in a liter of water. So those numbers would be the same. But then when they go into solution, here we would have 2 times Avogadro's number of particles. Here we would have 3 times Avogadro's number of particles. So there's more particles here than there, even though those are initially the same. Is that okay? Okay. So guys, anything else you want to explore there? Y'all good? Okay. So now guys, this is a skill that you need to have. Actually kind of a concept, but we are going to think our way through this. This stuff, guys, you want to write down. This is something that the AP gods expect you to be able to do. And for those of you that are in lab, this is something that you will be doing. Guys, these are what are called dilution problems or dilutions. So, guys, this is the way this goes. I'll just let these be enough for now. So, guys, up until this point, whoa, these are really fogging. I'll put them on when I need them. Guys, up until this point, lab for you has been this mystical, magical process where you guys walk into lab and, oh, look, surprise, all the chemicals that we need. Well, guys, not surprisingly, those chemicals aren't like manna from heaven. Somebody had to prepare those solutions, and that somebody's this guy. So guys, when I go into the stockroom to prepare solutions, they usually get prepared in one of 2 ways. It's either a solid dissolved in water, or it is a liquid being diluted. So guys, this is where we need to pick up the conversation. When is it a liquid that's being diluted? And the answer is this. Guys, when I buy acids, and if you think about it, we use sulfuric acid, hydrochloric acid, and nitric acid as our primary strong acids. Guys, when I buy acids, I do not buy them at the concentrations that we need to use in lab. So guys, when I buy these acids, they actually come to me saturated. This is sulfuric acid, the strongest it can possibly be at room temperature and room pressure. Guys, this is it. This is the limit to how strong sulfuric acid can be. 18 molar. You get this on you, you're done. I hate this stuff. Guys, you're going to find out that when we start doing labs where we need these concentrated acids, guys, my whole demeanor changes. This stuff is awful, awful, awful stuff. So here's the question. Why would I buy acid as 18 molar acid when I could also buy it as 0.01 molar acid, which is the stuff that we need in lab? So why do I buy it scary when I could buy it diluted the way we need for lab?
Because, you can make it less, but you can't make it more.
You can make it less, but you can't make it more. That's true. But if you think about it, we typically use 0.01, 0.1, and 6 molar acids. Those. That's the secret. Guys, this stuff is stupid expensive to ship. So when they ship me a bottle of concentrated acid, the box that it comes in is about this tall and it's about this big. And literally, it's the bottle packed inside a styrofoam sleeve, stuck in a box full of vermiculite, which are actually these little pellets that should this ever break, it absorbs all the acid. And then, guys, they have to security ship this stuff. And so it costs 3 times more to ship this stuff than it does the stuff itself. So it doesn't matter the concentration. If they're shipping me 0.1 molar, crazy expensive. If they're shipping me 18 molar, also crazy expensive. So I buy it concentrated and then I dilute it. But guys, here's the thing. I've been teaching 28 years. This is my second bottle of sulfuric acid. 3 decades, 2 bottles. Again, 28 years, I think I'm an extra hydrochloric acid bottle because we use that more. But guys, the bottom line is this stuff lasts forever. The question is why? Well, we're going to figure this out, and you need to be able to do this. So guys, this is stuff you need to write down carefully. You need to learn to solve what are called dilution problems. Guys, these are the problems that I have to solve when I make your acid solutions. So don't write this part down. So guys, mostly when we use acids, especially in lab, they are bought in concentrated form and then they're diluted. This is done by doing what's called a dilution ratio. Guys, write this down. Mi times Vi is equal to Mf times Vf. This is an equation that you need to know. It is not on the AP equation sheet. They assume that you can just think your way through this. But guys, you need to know how this works. So here we go. I don't think you need to write this down, but we are going to solve it. So it says this: stock sulfuric acid solution is 18 molar. How would you use this to create a solution to create 250 milliliters of 0.1 molar sulfuric acid? So guys, we're going to solve this together. Join me in the calculation. So it goes like this. Let's get our equation. MiVi is equal to MFVF. So guys, the I's are initial, the F's are final. So let's plug in our numbers. What is the initial molarity of the sulfuric acid? 18 molar. I lovingly call that Satan juice. Now guys, well, did I tell you? No, I won't tell you the story. No. It's at... so briefly. So you probably noticed, well, actually it was a different bottle. I'll keep it really short. 10 years ago when we built the new school, some of you may have lived in the neighborhood. Were any of you part of the moving process? When we moved from the old to the new building, literally what happened is every ward and stake in this area, they basically made it a huge work day. And guys, literally one day, it was a Friday, all the hundreds of people took the day off from work. And guys, we just ant marched every single thing from the old building into the new building. Desks, tables, computers, all of my chemicals. Guys, they all literally just neighbors came and helped us move. It was kind of like really cool. But it was also really sad because I believe he's passed now. There was an older gentleman who used to be a chemistry professor at BYU, and he wanted to especially help me move my lab, which was awesome. But he was along in years, didn't walk well, was losing coordination, and he was carrying a bin that actually had 2 bottles of 18 molar sulfuric acid in it. And he made it all the way to my lab and went to set it down on the counter at the front of the lab and missed. And he let go of the thing when it wasn't above the counter and it fell. And one of those bottles just blew up. It shattered. And it was, I don't know, somehow or another it didn't really get on him. But it got all over the counter. It started eating holes in the floor. And all of a sudden, I wasn't even there when it happened, and all of a sudden, the walkie-talkies light up. Find Knappenberger, emergency in his lab. I was like, oh, crap. So I come flying up here, and this poor old guy was just like, I'm so sorry. And I'm like, are you okay? Anyway, you'll see if you go next door, if you look really closely, they tried to refinish the front of my counter, but it still looks wrong. And you'll notice that at the front of the counter, the tile doesn't quite match. It's because it ate holes in everything, and they had to replace it. Anyway, let's keep going. So guys, back to this. What volume do we need? Well, that's our X. We need to know how much of the Satan juice we need to make the solution we need in lab. So guys, what is our final molarity? 0.100 molar. And then the final volume that we need is 250 milliliters. So let's do the math. So we've got 250 times 0.1 divided by 18. What, two significant digits? 1.4 milliliters. You starting to get it, y'all? Yeah. Why is it that I only have to go through like a bottle of that every decade? Well, guys, in order to make a quarter liter of 0.1 molar sulfuric acid, you get this on you, it still lights out. This is really concentrated. Its pH is actually like 0.3. It's even more acidic than pH 1. Like it's no messing around. But guys, I only need 1.4 milliliters of that stock solution. It's actually really hard to measure. I have to do it with a pipette. Because remember, a milliliter is just a centimeter cubed, right? And all I need is like 1.4 of those. But we're not done with the problem. Because what is the question actually asking you to do? How would you make this? Guys, I'll be right back. Okay, so guys, let's do this. You need to know this word for word. Write it down. So guys, all that you have done so far is done some math. The question says, how would you create this solution? And that's different. So guys, you need to know these steps, and you need to know them in the right order. You also need to know how to tell the AP gods as they're grading your tests that you know what you're doing. So ready? The question that we're now going to answer is, how would we make this solution? Ready? Step 1, put on PPE. A year ago, I couldn't say PPP out loud to people because nobody knew what PPP is. But in the days of COVID, do we all know what PPP is? Personal protective equipment. It basically means goggles, lab coats, and gloves. But you can just say PPE. So step number 1, don PPE, put on PPE. If you don't say it, you don't get any points. You've got to start with your safety stuff. Then guys, let me explain to you, big picture, how to make this solution. Have you ever met one of these? Guys, this is what is called a volumetric flask. These things are really cool and really expensive. This is like 40 bucks. So let me explain to you what we're looking at. This is like a graduated cylinder that is a one-trick pony. Guys, most graduated cylinders can measure in graduations, right? This guy has one line and it's right there. That's it. Guys, the only thing that this thing can do is measure this much stuff. So how much is it? It's on the side. It's 250 milliliters. But guys, it's crazy accurate. These things, ready, have been calibrated. How did they calibrate them? Well, guys, in lab, how did we calibrate our pipette? What did we do with the water so that we knew exactly how much we had? We weighed it, right? And then we used the density based on temperature to figure out the volume. Same thing here. And they have to do every one individually. That's why these things have got this really long spout. Because, guys, they know that the bottom of this is about 250 milliliters. But they are actually not perfectly cast. So they know that 250 milliliters is going to fall somewhere in this range. So what they do is they get distilled water, they measure the temperature of the water, and by doing density as mass divided by volume, they figure out the mass of water that will have a volume of 250 milliliters. Then they put this on a balance, This is all automated, but they put it on a balance and they add distilled water to this until it weighs out to like 5 decimal places. They add water to it until it weighs exactly what it should weigh to have 250 milliliters in it. Then, guys, what happens is this robot comes in and laser etches a line at the bottom of the meniscus of that mass of water, and now we know exactly how much 250 milliliters is. That's what makes these so expensive, is each one of them goes through that calibration process. So you'll see when you grab these, some of the lines will be up here. We're somewhere in this range, though. So, guys, with that said, this has a name. It is called the Volumetric Flask. So what was step 1? Put on PVE. Step 2, partially fill a volumetric flask with distilled water. Step 1, PVE. Personal protective equipment. Partially fill volumetric flask, distilled water. Now, guys, obviously I'm sort of chicken scratching a little bit, but you have to know volumetric flask by name, and if you don't say distilled water, you're wrong. Okay, now step 3. Carefully add 1.4 milliliters concentrated sulfuric acid, or you could actually identify it by its molarity. Either is fine. Step 4, mix, or you could just put swirl. And then step 5, add distilled water to mark on flask. And that's it. But now, guys, there's... Oh, go ahead. Well, not if you needed a liter, right? So we have them in 50s, 100s, 250s, and thousands. So they and you'll see, we'll start using them in lab pretty soon. They're all in the back corner there. But yeah, they come in common sizes. They wouldn't have like 80, but they come in common volumes. Yeah. So, guys, one important thing to talk about, and then we're going to move forward, and it's this. This is critical. If you do this step first, this is bad, bad, bad. And not only is it bad in terms of you won't get points on the test, this could get you seriously hurt. So, guys, this is the idea. When you dilute acids, here's the rule. You always add acid to water. You never add water to acid. And guys, let's talk about why. When this acid dilutes in the water, it's not just dissolving in the water, it's reacting with the water, right? What is that reaction reviewing for the test? When acids go into water, what is the reaction that's taking place? What's the acid doing? Not quite hydration, because that's a physical change. This is a chemical change. So, guys, hold on. So what is the acid doing in water? Giving away hydrogens. Where do the hydrogens go? To the water to form what? H3O, which is hydronium ion. Guys, that is not a physical change. That is not hydration or dissolving. That is a reaction. Literally, you are forming bonds between protons and water. But guys, here's the thing. It is freakishly exothermic. Like if I were to take, I don't know, half a liter of this and half a liter of water and just dump them together, it would boil. This is like crazy exothermic. And so guys, you'll see when you start diluting acids, even 1.4 milliliters of this concentrated acid into water, you can feel it get hot. But here's the trick. Guys, imagine if we did this backwards, and I'm going to just over-exaggerate this. Imagine if we wanted to dilute this acid, and I just screwed the lid off and started dumping water into it. It's going to get really hot, and it's going to boil. And when it boils, it's going to turn into a geyser, and it's going to shoot all over the room. But guys, when that happens, what is coming out of the bottle? Mostly acid. You don't want that on you. But now, guys, imagine that we go the other direction. Imagine that we take a big old bucket of water, and then we start dumping acid into it. That's also going to get hot. And if it does go out, what's coming out of there? Mostly water. Do you see the difference? Guys, you always add acid to water and not water to acid because the water that's there acts as a heat sink. It absorbs the energy of the reaction, and if it does erupt, most of what's coming out is water and not acid. Do you see the distinction? So guys, you always add acid to water, you never add water to acid. Yeah? No, because that's not a chemical change. That's a physical change. I mean, yes, in that it's a geyser, but the heat at Yellowstone is just geothermal, right? Hot rocks that boil water. This is a chemical thing that's giving off, but you still get a geyser. Yeah. Then what? No, because remember, even 18 molar sulfuric acid is still mostly water, right? So they absorb heat similarly. The difference is that you want most of what's absorbing the heat to be water and not acid. Is that okay? So guys, how are we doing? Is this sitting okay? Okay. I just made an executive decision. Guys, I don't think that we have time to get into titrations. I'm going to take it out of the test. It's totally fine. Frankly, it's typically sort of an afterthought just to reconnect you. Guys, the one drawback to this is I won't then be able to show you the software that I was going to share with you. In lab, we will actually leverage virtualization software frequently. Let me just show it to you briefly, and then... Well, we did. If you look here, Spencer, when we added the acid, that's step 3. And then we fill it the rest of the way up with the water. You okay? But now it's dilute acid, because you start with a lot of water, put a little bit of acid in it, now it's dilute. Now when you add more water to that, it's already diluted.
So you add water first, and then you add what you need, and then you try to get it up.
Good for that's exactly right. Yep, you got it. Yeah, are we okay on that? Okay. So guys, let me just show this to you. So I'm just going to, let's do this. Here's your homework. So 59, 64, 67, 75, 79, 85. Don't do the problems that are about titration. So again, guys, 59, 64, 67, 75, 79, 85. So guys, I don't want to waste your time, but I do want to at least show this to you momentarily. Donnie, did you have a thought? Yes. And so It's actually funny. Of the last 7 labs that we do in this class in third period, 6 of them will be titrations. Yeah, we titrate like crazy. So guys, let me just briefly show you this. I don't expect you to learn anything from this, but I at least want to show you what titrations look like. So this software that's launching, hopefully. So the software that's launching is actually a software package called Virtual Chem Lab. It was written at BYU on a National Science Foundation grant. This has been around for about 15 years. I was one of the testers as they were originally launching this software. It was originally done in-house at BYU. Then they actually sold it to the people that make our book. And it's gone. Really? Is it not in this one? Guys, it used to be that our books in the back had a sleeve where there was a Virtual Chem Lab disc that was there. I guess they've done away anyway. So the book company bought this from BYU, but then guys, the book company just put it on a shelf and let it die. As you can see, they don't include it with the book anymore. So the professor at BYU that wrote the software, Dr. Woodhouse, one of the two, he actually brought it back in-house, started a company, and they're sharing it again. Guys, all of this to say, if you're headed to BYU, you're going to get really good at this software. And as a matter of fact, I got an email from Addie Beaslin a couple of weeks ago, and she was like, thank you for teaching us how to use Virtual Chem Lab because of COVID, my lab, my Chem 107 lab at BYU is not in person at all. The entire lab is being done through Virtual Chem Lab. The whole thing. But guys, with that said, let me just show you briefly how this works. And then we will use this significantly in third period. So guys, in order to do this, we're going to go to the Titrations Bench. And when we click on that, it's actually amazing what they did at BYU. All of this is virtualized, but all of the chemistry is real. And so as you go through and do labs, guys, actually everything that you see is actually what happens when you do the lab. So let me just show you quickly what titration looks like. Again, you don't need to know any of this. But guys, in order to do a titration, what you need is an acid and you need a base. And then when you go back into lab, what you do is we typically use the base as the titrant. So we pour the base into a burette. Then what we do is we get a beaker and we put the beaker on a stirring plate, and then we measure out some hydrochloric acid. We put the hydrochloric acid into a beaker and we turn this on and we let it stir. Then what we have to do is we need to add an indicator to the acid. And then guys, as we add base to the acid, the two are neutralizing each other. What you'll see is that eventually this thing will turn pink. It turns pink when the bases neutralize the acid. And now that this thing is pink, guys, by reading this volume, we can actually calculate the concentration of that acid out to 5 significant digits. That's what this process allows you to do. What it allows you to do is by knowing the concentration of one solution, in this case the base, it allows you to figure out the concentration of another solution, in this case the acid. And guys, we're going to be doing a bunch of these in lab. The thing that's amazing is if we had done this lab, it would have taken about half an hour, and I did it in about 90 seconds. So this virtualization stuff, guys, is actually really, really slick. And there's all sorts of stuff we can do. We can go into the inorganic lab, and we can go into the stock room. Well, first we need a test tube. We can go into the stock room and we can go in here. Actually, let's do this. We can go into the stock room and we can grab a test tube and we can put some silver in the test tube. And if we look right here, you'll notice that the silver solution is clear. But if we come along and if we add some salt to this, oh my gosh, we just formed a precipitate. That precipitate is silver chloride. What we can do then is we can centrifuge this, and now the silver chloride is at the bottom, and then we can decant this, and we can actually pour off this precipitate, and now we're left with nothing. Anyway, all sorts of really cool chemistry that we can do, and this is actually pictures of how it all actually would look. So we're going to fiddle with this more later. And if we go into quarantine, we're actually going to be doing some of our labs on here. So all of that to say, guys, we are not going to put this on the test. The test is Monday. Do the little bit of homework that you can. We've got about 10 minutes left. That's going to do us for the day. So there you have it.